In today's video, I'm going to be using Pandas, NumPy, Seaborn, Matplotlib, and scikit-learn to analyze this dataset here, which will be linked below. Let's start out with some imports. So I'll say imports, spelled that wrong, import NumPy as NP, import Pandas as PD, import Matplotlib.pyplot as PLT, import Seaborn as SNS, import warnings to get rid of those annoying warnings, filter warnings, ignore. I will do the better spacing there, can run that. It's nice. So we're going to read the data, so we're going to say df, I will first just type load in the data is equal to pd.read_csv global disaster response 2018-2024.csv. Pretty long name, but that is okay. Now we're going to do inspection. So we're going to do df.head to get the first 5 rows and take a look. So we have date, country, severity index, casualties, economic loss, latitude, recovery days. So pretty rich data, lots to go over, so that is pretty good. Now you're going to say basic statistics/summary. So df.describe, spelled that wrong. And I will do .round2 for more readability. And as you can see, we have the average, the quantiles, the amount of values. So I'm not going to go too in depth into this, but it is pretty useful. It is there if you want to pause and take a look at this. So now I want to do check column types in case we have any columns that need to be converted. So df.info. Let's see, we have date as an object, which is not good. I have to change that. Country's an object, floats, integer. So everything looks pretty good besides the date. And you will see we have 50,000 columns up here. So pretty big data set. Just going to say fix date convert to date time. So we can do df date is equal to pd.to date time. Pass that in again. And if you go back up here, we're going to see, hopefully, that is now a datetime object. And since it is, we can extract the year, month, and the day. So we're going to say extract features. So df year is equal to df date.dt.year. And same for the month and the day. Day, month, day. And I will run df.head again to show you that. So we have the year, month, and day extracted. Definitely going to be using these later on in the analysis. Now I'm going to do check null counts. So df.isnA.sum, see our null values. And fortunately we have none, so that is pretty good, pretty clean so far. But we also want to check for clean's sake, check for duplicates. So df.duplicated .sum, I think I spelled that correctly. And yeah, we're gonna have 0 duplicate values, which is pretty good. Now what I'm gonna do is I'm gonna say select all numerical columns for histograms. So I'm gonna be selecting these columns and making histograms out of them to show distribution. So I'm gonna say num_calls is equal to df.select underscore dtypes include equal to number dot columns dot to underscore list. Now if I go ahead and run that, I'll show you. We have all the numerical columns selected. So now, as I said, we're going to convert all these to histograms. So the first thing I'm going to do with a pretty simple formula is calculate the amount of rows I want. So rows is going to be equal to the count of num calls plus calls minus 1, and then select all this, floor that by calls. So with this formula, you're always going to have the correct number of rows. Now you could like manually count all of this and like figure it out yourself, but that takes a long time, so no point in doing that. So now I'm going to say fig axis is going to be equal to plt.subplots, pass in rows, pass in calls, to say fig size is equal to 5 times calls, 4 times rows for a pretty good fit. Actually can run that and see everything now. So we have 12 plots, pretty beautiful. So now I'm going to do axis is equal to axis.flatten, and I'll explain why I did that in a second. But first I'm going to go ahead and do for index call and enumerate num underscore calls sns.hisplot df call td equal to true, bins equal to 50, axis is going to be equal to axis I. So pretty much what's happening here, I'm looping through num calls, getting its index, and I'm saying axis equal to axis I. If I didn't flatten axis here, I would have to pass in a 2D matrix, like something like this, like ij, do like a nested loop for j and enumerate calls. It's just not gonna, it's pretty complex, there's no point for that, so just flatten it. And as you can see here, once it loads in, it might take a little bit. Come on. Yeah, okay, we're gonna have all of our histograms for our numerical columns. So pretty good info here. And I will go ahead and add a title for more accuracy. So axis I.set underscore title, f-string distribution of call, and I have to do plt.title layout. Otherwise, the titles will be overlapping with everything, and that is not going to be aesthetic at all. So plt.show now, and we're going to have pretty beautiful titles with an accurate title. They're pretty beautiful plots, that is. Let's go ahead and see. Yeah, there we go. So we have nice plots now. We can see some of our data is normally distributed. Some of it is skewed. So we can take a look at that in a second. Down here we have latitude, recovery days. So yeah, pretty good, nice data here. So now I'm going to do create a function for outliers. To do this, I'm going to say def outliers, pass the data frame in, pass a column in. I want to say q1 is equal to df.call.quantile 0.25. I'm going to be using the IQR method here. And then 0.75, specify our IQR is equal to q3 minus q1. I'm going to say lower underscore bound is equal to q1 minus 1.5 times our IQR. Same thing for upper bounds, which is changes to a plus sign, q3, and then upper. Now I'm going to say return lower, or no, df call less than lower underscore bound, or df call greater than or upper bound to check for outliers. So I'm going to put that in parentheses because you have to. Parentheses, and I'll say, for example, maybe outliers df, let's just do casualties. So casualties, hopefully I spelled it correctly. Is it the U before? Yeah, hold on. Casualties. As you can see, we have a Boolean index, if you will. So what happens is I'm passing in df casualties into the data frame. It's going to scan every single row and apply this condition to it. If it's false, it'll return false. If it is true, it'll return true, marking it as an outlier. Now what I can do is say mask is equal to this, and do df mask to check for our outliers. So all of these rows have a casualty number that is an outlier. So 280, 342, 370, that's quite a lot. A tornado, wow, that is pretty scary. So now what I can do is I want to be the skew. So as earlier, I'll scroll back up. There's a bit of skew in the data. Some left skew, right skew, dot here, response efficiency. So to reflect that, we can view, say, skew is equal to df audio all the columns, so num calls dot skew. And I'll also do kurtosis, so df num calls dot kurtosis. Put it in a data frame for readability. So say skewness, skew, kurtosis, kurt. Did I spell that wrong? Oh, I didn't do a colon. So as you can see, we have the skewness and kurtosis, which does match our data. So for response time, we have a 1.9, and a 5 for kurtosis. So we can kind of go back up to our histograms for response time. What is that right here? And yeah, it does reflect it. It is right skewed, which makes sense according to our data here. We will be fixing some of these columns later in the feature engineering part, but for now we're going to continue. So I'm going to say df.head to look at our data. So we show the distribution of the numerical columns. So I'm going to show the distribution of our categorical columns. Sorry. We have country, disaster type, and let's see. I think that's all. Yeah. So I'm going to say show distributions of categorical columns. So I'm going to say fig axis is equal to plt.subplots. We're going to do a 2x1, and then fig size is equal to 10x9. No need to like do a loop. We only have 2 columns. No need to do anything else. So we're going to say sns.countplot df. Let's just do country. We can say axis is going to be equal to axis 0, and I will paste that down here. Axis 1 df disaster type. Get some plots now. And this is kind of ugly, but I will be fixing that. So we have our distributions down here. Before I analyze it, I will go back up here and make this prettier. So I'm going to say palette is equal to set2. Do anything you want. I like set2 quite a lot though. Give it a title. So I'm going to say axis 0. That's an O. 0.set title distribution of countries. Can I spell correctly? Okay. Same thing for down here. Axis 1 distribution of disaster type. I will do plt.show to get rid of this little label down here. plt.show. And as you can see here, we have a nice, beautiful graph. So the data for both of these is pretty evenly distributed. Like maybe Brazil has like 50 more countries on average, or rows on average than other countries do, but pretty evenly distributed data here, so pretty diverse. Definitely pretty good. So now we're going to step into some univariate, variate analysis. Make a violin plot with box plot inside. So first thing we're going to do is going to be picking some columns. I could do every single column in numerical columns, but I'm going to pick 3 maybe. So I'm going to say uni calls is going to be equal to, let's do severity index, casualties. What just happened? Let's just pick one more, maybe economic loss. That's pretty interesting. So I'm going to say fig axis is going to be equal to plt.subplots. Let's just do a 1x3, and then fig size is going to be equal to, let's just say probably 15x5. Then I'll do for index call and enumerate uni calls sns.violin plot df call axis is going to be equal to axis I. So by default, a violin plot has a box plot inside of it, as you can see here, but it is a bit ugly. So to change that, we can do inner is equal to none to get rid of that, and then do sns.boxplot df call axis is going to be equal to axis I. And let's see here. So once again, it is pretty ugly, so change the width to be equal to 0.15, maybe color equal to sky blue, and then maybe like up here, color equal to light green. So yeah, pretty more aesthetic now. And I would just say axis I.set title f-string distribution of call. Same title as the histograms, but both are accurate, both describe what's going on. So a lot of outliers and casualties. We did see that. How many rows were there? There were 889 rows for casualties and outliers, so quite a lot. That is all reflected right here. So now, next thing we can do is do some correlation analysis. So I want to say correlation matrix. So I'm going to say SNS, go back up here, SNS.heatmap df noon calls dot core, and I'm going to say not is equal to true, CMap is equal to yellow, orange, red. So now we have a heat map. I will fix this to make it more readable. plt.figure, fig size is equal to, I would say a 10 by 6 would be good. plt.title, correlation matrix, and then do plt.show. Nice, that's more readable. So as you can see, we have our correlations of everything now. Not many correlations with like latitude, longitude, year, month, and day, but for example, recovery days and severity index are severely correlated. Severity index and what is that? Aid amount severely correlated. So get a pretty good idea of how our data is correlated here. Really helpful. So to kind of visualize all this, I'm going to do a pair plot. Now pair plots are very massive, take a long time to load, so I'm not going to include columns like latitude, longitude, year, and month and day, because it'll take too long to load and it's going to be really overwhelming. So I'm going to say pair calls is going to be equal to call for call in noob underscore calls if call not in. I'm going to say day, month, year, longitude. Did I spell that correctly? Latitude. Let's see if that worked. It did. I'm going to say now sns.pairplot, df pair underscore calls diag underscore kind is going to be equal to KDE. Like with histograms, I'm going to run that. It will take maybe like 10 seconds to load because it is kind of big. It would be like way bigger if these were included, so thankfully they're not. Let's see here. Wow, it's taking quite a while. Yes, here we go. So now we have scatter plots for every single combination of numerical columns. So as you can see here, this top right is going to be severity index, and I imagine recovery days. Yep. 0.97 correlation. We can see a negative correlation here, negative correlation, positive correlation, like a low correlation. So pretty interesting data here. And yeah. And as you can see, there's a lot of points. There's 50,000 points on each one of these, so there is quite a lot closer together. So now that I have that done, I'm gonna go down here, do df.head. I want to see something like use our maybe like year column. So I want to see maybe response time over the years. So did we improve our average response time by the year? So I'm going to say copy paste this here. So df.group by year, zone in on response time dot mean. As you can see here, have all of our values, and I will be making a line plot. So I'm going to say plot data equal to that sns.lineplot. We're going to say x is equal to plot data dot index, y is plot data dot values. And yeah, as we can see here, the answer is no. Response time pretty much stayed constant. I will make this a little bit better. So plt.show, plt.title, response time over the years, capital T. That's not good. Okay. So yeah, it stayed pretty constant, and we can do markers equal to an O, and even do a plt.grid, which is really overpowering on itself. I'll show you that. The lines are kind of, I'd say, too big, so I'm going to say alpha is equal to 0.3 to kind of make them more transparent. So yeah, pretty similar. In 2020, we had less average response time. 2021, the highest response time, but it was all pretty similar, all within 12. So, okay, I'm doing some feature engineering now. So feature engineering, I will do, or have a reference, so df.head. Run that. Maybe I can do something like average severity by country, so df mean country, copy that, underscore severity index is equal to df.group by country, zone in on that. We can use dot transform here and do mean. So what that'll do, it'll put the mean severity index by country on each row. So 5.04, 5.04, which is going to be Brazil. And next we can do something like, let's see, group casualties by maybe like high, low, medium. So I'll just do df casualties level, maybe with a Y. Nothing too serious, not going to go too in depth into this. So I'll say pd.qcut df casualties. I want 3 different labels, so quantiles equal to 3. I think that stands for quantiles, I'm not actually too sure. I'll do low, medium, high. This is going to divide casualties into low, medium, and high, so I will control enter that and check. So yeah, we have medium, low, low. So all of these were low casualty levels. So now what we can do is we can say maybe fix like a something that's kind of skewed. So I will go back up here and I would say response efficiency. There is a pretty big skew going on here, so I'm going to be doing an XGBoost model, so it's not strictly necessary, but then again, it does not hurt. So I will say to fix it, I can do something like max underscore val is going to be equal to, let me get the name, response efficiency score is equal to dot max. I can do df response efficiency score log is going to be equal to np dot log 1p max underscore val minus df response efficiency score. So and just that's going to work. So whoops, let's see if I run this again, we're going to see, yeah, we have 2.8, 1.5, so pretty good. Like I said, I'm going to keep it kind of small. I'm not going to do too much feature engineering because just really kind of over the top. So I'm just going to go ahead and start with our sklearn imports. So this is going to take a little bit. So from sklearn.model underscore selection imports train test split. And I will do grid search to CV in a little bit, but for now I'm going to leave that out. From sklearn.metrics import mean absolute error. And then R2 score, so R2 underscore score from sklearn.preprocessing imports, let's do one hot coder from sklearn.compose import column transformer. And I will be doing a pipeline for this for minimizing leakage, etc. So from sklearn.pipeline imports pipeline. And then finally from XGBoost imports XGB regressor. Hopefully that all works. Perfect. So yeah, as I said, I'm going to be doing maybe like a random grid search later, but for now, I'm just going to build the model. So I'm going to say our x is going to be equal to, let's pick a y first. So I think I saw recovery days was pretty interesting to me. So yeah, let's go over here. We have recovery days right here. See, I want to try to predict recovery days given all of this data over here. So I'm going to say x is going to be equal to df.drop recovery underscore days axis is equal to 1. Y is going to be equal to df dot just recovery days actually. So and then we can do numerical columns is going to be equal to x.select underscore d types. Include is going to be equal to number dot columns dot to underscore list. Same for categorical. A bit different, obviously. So categorical. We can just do object. And now we can go ahead and build our preprocessor. So preprocessor is equal to column transformer. Transformers is going to be equal to, for our numerical columns, we're not doing anything, no impeding, no scaling, so we could scale, but given XGB, our model we're using, there's really no point because it handles that kind of data already pretty well. So we're going to say pass through and then pass these columns in. For our cat, we're going to do a one-hot encoding, so one-hot encoder to assign the values with sufficient things. So we can do handle unknown equal to ignore, always a good practice. And then yeah, run that, make sure there's no errors. Nice. Now I can say pipeline is going to be equal to pipeline. Steps are going to be equal to, we're going to say pre-process, comma, pass in preprocessor. Then we're going to say XGB regressor. For now, no hyperparameters. I will be doing that later on in the video, but for now we're going to start off with nothing. Make sure there's no errors. Okay, we're going to say X train, X test, Y train, Y test is going to be equal to train test split X comma Y. We can say test size is going to be equal to 0.2. And again, random underscore state equal to 42. Now we can go ahead and fit our pipeline. So pipeline dot fit X train, Y train. We can go ahead and show that, or do prediction actually. So prediction is going to be equal to pipeline dot predict, pass in our X test. Run that. Let's see. Okay, nice. We're going to say R2 underscore score is going to be Y test prediction. Same thing for our mean absolute underscore error. We're going to say Y test. Can I spell? Okay, prediction. Oh my god. Okay, prediction. What is wrong about that? Okay, prediction. Okay. Let's see here. So we got a 0.93 and a 4 for the mean absolute error. So our model explains 93% of variance, which is pretty accurate. So pretty good model so far. Okay, so now let's go ahead and add random. Okay, what happened to my art? Randomized search CV. Add that in. Now we're going to go ahead and specify a param grid down here to try to make this model a little bit better. get some space, we can say param underscore grid is going to be equal to, let's go ahead and start with xgb in, is that 2? Underscore estimators. We're going to say, outside of that, we're going to say, let's do 100, 200, 300, comma, xgb max underscore depth. We're going to say maybe 3, 5, and 7. Now we're going to say xgb underscore learning underscore rate is going to be, let's just do maybe 0.01, 0.05, and then 0.1 for 0.10. And then after that, we're going to do xgb underscore sub sample. That is going to be, let's say 0.7, 0.8, and then 1. So we're going to do 2 more. Let's just do xgb underscore call sample by tree. That should be fine. It's going to be, once again, just this whole list. So now for our last thing, xgb underscore gamma. That's just going to be 0. Can I type 0, 1, 5? Okay, now what we can do, we can say, go down here a little bit. So just to say our search. Okay, why is it not scrolling down? Search is going to be equal to randomized search CV. We're going to do estimator is equal to our pipeline. Param underscore distributions is going to be equal to our param grid up here we just made. Param underscore grid. We're only going to do, let's say, 50 iters. So iter is going to be equal to 50, and that's going to be in underscore 3 CVs crossfolds. So we're going to do scoring. We want to make our R2 go up. So R2 verbose is going to be equal to 2. In jobs is going to be equal to -1. And then finally, random state, so it's equal to 42. So now what we're going to do is we're going to go ahead and fit our data on this search now. So search.fit search, down here, dot predicts. And we can go ahead and just over here say prints maybe like best params, and say let's do like an f string. You don't have to actually, but search dot best underscore params underscore, and then same thing for score. So best score this time. Change that to score, and then down here, once again, we can go ahead and do. Well, we can just save that for now. It's gonna auto mistyped param distributions. So fix that or run that again, and I will let that load. They're also up here. Now we can rerun this down here. And yeah, we went up by like 0.04, so it wasn't too significant, but okay, so now we're gonna go ahead and get our estimator importances. So to do that, I'm gonna say preprocessor is equal to search dot best underscore estimator dot named I think there's a underscore here, named underscore steps pre-process. Make sure that works actually. Perfect. Now I can say new features is just going to be equal to our numerical columns because we've already done that. There's no changing there. But for cat features, we need to actually go back to our preprocessor dot transformers underscore one, get out our country and disaster types. So dot get feature underscore names underscore out, and then pass in categorical underscore columns. And then we can just say, so maybe like all features is going to be equal to a list of new features plus cat features. So a list of cat features. And get our model out. So XGB model is just going to be equal to search.best underscore estimator underscore dot named underscore steps. XGB, quite tedious with all these little dots and underscores, but that's fine. And we're going to say importances is going to be equal to XGB underscore model dot feature underscore importances. Make sure there's no errors. Perfect. Finally, we can make a data frame showing all of our results. So what feature was the most important? We're going to find out. We're going to say feature, and then that would be all features, and then importance, that would be importances. We're going to go ahead and sort underscore values by is equal to importance. Ascending is going to be equal to false. I think I have to do a string here, so oops. Importance. Run that. And yeah, so we can see that. Okay, wow, so severity index was pretty much the determining feature, the only feature that was really relevant. Response time mattered very, very little. You can see here that, okay, so some features just like mattered like none at all. So Bangladesh had literally no impact on our R2 score. So yeah. So thank you for watching. Please like and sub if you want to see more portfolio projects like this, and I will see you in the next video.